Dear students, now we will discuss about the relation between SHM and circular motion. In the previous classes, we have seen the kinematics of SHM, that is position, its velocity, its acceleration, etc. And we will derive this formula today with the help of circular motion. In the previous lecture, I have derived all the formula, all the equation which are function of x and function of t also. That the position of the particle, the acceleration of the particle, the velocity of the particle executing SHM. We have derived the formula from the force equation or the differential equation of motion. But today I like to derive the expression using the circular motion. And we will see that the projection of the circular motion of a particle onto the diameter will be actually the circular motion. So let me draw the diagram first. So let us consider a circle, and the circle has a diameter 2a, or the radius of the circle you can say is a, and the particle at any instant at that point. Now let me consider that the particle from this point to this point will go after a time interval t, and if the angular frequency of the circular motion, the angular velocity of the circular motion is omega, then this angle will be omega t. So the particle which is going from this point, let us consider this point is p and this point is q, and here the radius of the circle is a. Now if we see that the projection of this point onto the base will be like this. So this is the point of projection of the particle, or the point of projection of the q point, that is q dash. Similarly, if we see all the projections at each and every point on the circle from this point to this point, when the particle is at this point, then the projection will be on that point. When the particle is this point, then the projection will be at that point like this. So the projections of all the instant of time onto the base, if we take it, then we can easily see that the projection of this particle will go along the diameter of the circle like this. You can see from the figure that the projection at each and every point on the circle will lie on the diameter of the circle. And if we concentrate on the projection of the particle, then we can easily find that the projections of the particle will displaced along this diameter. So here the actual particle which is moving around the circle along the circumference, then the projection of that particle will go along the diameter of the circle. And when the particle will again traverse from this path, when it will be at that point, then the projection will be at that point like this. The projection of each and every point we can easily find out like this. So we have seen from this diagram that the projection of the particle going from p point to p dash point, and again it will come back from p dash point to p point. So when the particle will execute a complete rotation from p point to p point, then its projection will go from p to p dash and again come back from p dash to p. So it will get a complete SHM, or a complete vibration, or complete oscillation along this diameter. So the particle which is executing circular motion, the projection of that particle will execute a SHM. So if we now concentrate on the projection of the particle which is going along the diameter, we will get all the information of kinematics from this particle. And when we derive the kinematics of the particles which is lying or which is going along the diameter, then we will derive already the kinematics of the SHM. Because the projection of the particle, the projection of this particle will go along this diameter, so it will execute a SHM. Now we will see what is the position of this projection of particle, and that position will be the position of the SHM, because this particle is actually execute SHM. So now let me derive the kinematics of this particle like this. If we again draw the circle like this, so this is actually the radius, and we will take the radius is A. Now if we take the anti-clockwise rotation, clockwise rotation in this direction, then the angle will be at that point. So after certain time interval t, it will go from this point to this point, and the angle will be here. Angle will be omega t. Now if you take the projection of this particle on that point, then this will be the anytime position from this origin or the point of oscillation, because the projection of this particle will execute SHM along this line about this equilibrium point. This will be act as equilibrium point. So the position of this particle with respect to this origin will be the displacement of the particle anytime t. So from this figure we can easily say that here x is equals to, from this triangle we can easily say that a sine omega t, because this angle will be pi by 2 minus omega t, and a and the projection of this a along this line will be a cos pi by 2 minus omega t, that will be a sine omega t. So this is actually the position of the particle at any time t, which we have earlier seen from the differential equation of motion. And when we take the solution of the differential equation of motion, we will get this also. And we have already seen in the previous lectures that we can get x equals to a sin omega t by using the differential equation of motion. But here, using the simple trick that the projection of the particle which is executing circular motion is actually the SHM along the diameter. And if we derive all the formula involving this particle which is going from this point to this point and this point to this point along the diameter, we will get all the results of the SHM. Similarly, if we want to derive the velocity of this particle, then we will have at that point the velocity will be along the tangent like this. At this point the velocity will be like v0, and the angle here actually this angle will be actually pi by 2 minus omega t. So this angle will be omega t. And now the component of v0 along this direction will be, if we take it as v, then v is equals to nothing but v0 cos omega t. As you can find that the component of v0 along this direction is v0 cos omega t. And here the particle, when the particle will go from this point to this point, if we take it p, then it will be p dash. So the direction of the velocity will be along the OP dash direction. So here we have taken the direction of V in this direction, and the component of this V0 along this direction is V0 cos omega t. And as you know from a circular motion concept that V equals to omega r, and here r is actually capital A. As you know that V equals to omega r, but here r is nothing but A. So V equals to omega A. Here V means V0. So this V0 will be omega A cos omega t. So this will be V. Similarly, if we want to know the acceleration of the particle, then the acceleration we know from the circular motion, the acceleration is always towards the origin or towards the center. And if this is A0, then the component of this acceleration for the circular motion, for the SHM, will be in this direction. Because you know for the circular motion that the acceleration is inversely, the acceleration is proportional to minus x. That is, it is opposite to the direction of position. So the component of A0, as this angle is omega t, this angle will also be omega t. So the component of this A0 along this direction will be A0 sin omega t. So here we can write that A is equals to A0 sin omega t. And this A0 is nothing but, as you know from the circular motion, that A equals to omega square r. Here r means capital A and A means A0, and there will be a negative sign because the direction is inwards. So if we talk about A0, then it will be minus omega square A sin omega t. So by comparing the SHM with the circular motion, or when you take the projection of the circular motion, executing circular motion particle along the diameter, we will get all the information of the particles from this diagram simply. And the position of this particle will be the position of SHM. The velocity of this particle along the diameter will be the velocity of the SHM. Similarly, case for the acceleration. So instead of solution of differential equation, we can get all the results, all the kinematics results that we need from the circular motion concept, or by comparing SHM and circular motion. Okay. Now here one thing you can see, that there is no phase difference or phase angle, you can say. Initial phase, there is no initial phase, phi equals to 0 we have assumed. So if there is an initial phase, then the case will be different. In that case, this figure will be something different, because the particle has an initial phase, that is, the particle will start at t equals to 0, the particle will be at that point. If we take, then for the first time when we take the projection of this particle, will be at that point. So there is always a phase phi, because in the previous case we have taken that the particle was at that point when it will start its motion, but here we have taken the particle is at this point at t equals to 0. Now from here, after certain time interval t, if it will go to this point, then the angle is omega t. This angle will be omega t. So the total angle for this case, this will be x, and for that case, then the total angle is phi plus omega t. So if we take this phi plus omega t as theta equals to omega t plus phi, then the projection of this A, that is the radius of the circle, and the projection of this A on this line will be A sin theta, and this theta will be nothing but A sin omega t plus phi. Is it okay? So this is x equals to A sin omega t plus phi. But here this phi is 0. So the initial phase phi is 0 for this case. Okay. But if there is initial phase, then at t equals to 0, the particle will start from this point. But if there is no initial phase, then the particle will start from this point. So the projection will be at that point. And here the initial projection is at that point. Okay. Thank you.